Hello everyone. Today I, Abhinav, Sahil Kumar and Sahijit Singh Bangar are going to represent this presentation on the topic Integrative Optimal Framework for Hybrid Power Systems, Design Analysis and Sustainable Solutions for Pilley Island, Newfoundland under the guidance of Dr. Mohsin Jamil. So for this presentation, I'm going to start with brief introduction of what this project is about. Then I'll narrow it down to the island specific information. Then after that, I'm going to explain the basic static analysis, and in further detail, Sahil will be explaining the static analysis. The dynamic analysis part will be explained or discussed by Sahibjit Singh Bangar. So what this project is all about. This this paper presents the design and analysis of a hybrid power system tailored for the unique energy requirements of Pilley Island, Newfoundland. It's located in a remote region and it faces challenges in terms of reliable and sustainable power generation due to its isolated location and the limited availability of conventional energy sources. So our proposed hybrid system aims to address these challenges by integrating multiple renewable energy sources with an existing conventional power grid. So our design process begins with a comprehensive assessment of the energy demand and consumption pattern of Pili Island. This data is then used to determine the optimal combination of renewable energy technologies using Homer Pro, considering the island's geographic characteristics, climatic conditions, and available resources. The dynamic simulation study is also done using MATLAB with a chosen hybrid system comprising of wind, solar, and a battery energy storage system along with a along with an existing diesel generator for backup power. So what this our project will do, it will create an impact and inform policymakers, energy planners, and stakeholders about the viability and benefits of hybrid power system for a sustainable and resilient energy future. So this slide represents everything about the island. It's a small island located in the eastern part of Newfoundland. It's situated in Notre Dame Bay, surrounded by scenic coastal areas and rugged terrain. In 2021, the population was 286 and there were 186 houses, and most of them were private dwellings. The energy demand, it varies seasonal. Uh, Winter months experience higher peak loads due to space heating needs, while summer months witness reduced energy demand. The total average daily consumption is about 2500 kilowatt hours, and after researching a lot, the potential renewable energy that is really suited for this island will be solar energy and wind energy. This is the proposed static system analysis for which we used Homer Pro. On this diagram on the left, we have a diesel generator CAT 410, 410 kilowatt diesel generator. Below that is uh, windmill. We have used 18 windmills, which will be generating each 30 kilowatt, and the last one is solar uh, with a rated capacity of 1161 kilowatts. Our average load is 2500 kilowatt hours per day, and we have a Tesla Powerwall 2 battery. We have used 174 batteries for storing excess energy and ensuring continuous power supply. Now Sahil will explain each component in further detail.
Thank you, Abhinav. From here, I'm gonna discuss about my presentation, and I am Sahil Kumar. I'm going to discuss about the simulation results for the PV array. Rated capacity 1161 kilowatts, the maximum power output under ideal conditions. The mean output we get is 158 kilowatt, average power generation over a given period. The daily mean output is 3785 kilowatt per hour, and the average, which is average energy produced in the kilowatt hours on a daily basis. The capacity factor 13.6%, actual energy output as a percentage of maximum potential output. The annual energy production 1385 kilowatt hour per year. And in the table you can see the minimum output is 0 and the maximum output 1271. The PV penetration was about 156%, and the hours of operation we did the simulation is 4,379 hours per year. The levelized cost is $0.0542 kilowatt per hour. The clip production 0 watts. The quantity, as I discussed in the above, are these the same. And this is on the right side in the graph we can see the solar irradiance, and which we can see that from March to October it is high because during this summer this is the only period where the Pilley Island get most of the sunlight. So this period we can use our solar or PV on the good production rate. Now coming to the simulation results for the generator. The annual electrical production from the generator was 21,249 kilowatt hours per year. The mean electrical output was 343 kilowatt, the average power generated by the generation. The minimum electrical output is 102 kilowatt, the lowest power level that generator can provide. The maximum electrical output is 410 kilowatts, the highest power that generator can deliver. So this is the total summary that what I explained, and in the table 4 from the Homer Pro. Now telling about the battery information. The total number of batteries we use is 174. These are arranged in parallel with one strings for increased storage capacity and efficient energy management. Each battery has a string size of 1, contributing to overall storage capacity. The bus voltage is 120 volt, determining the electrical potential at which the batteries operate and their compatibility with other components. And here we can see the average energy cost from the table 5 is $0.0241 per kilowatt hours, and some of energy in and energy output. The storage depletion is 507 kilowatt hour per year, and the annual throughput is 314696 kilowatt hour per year. So here are some simulation results for the wind turbine. The total rated capacity for our wind turbine is 540 kilowatts. The total production is 662 6,21,683 kilowatts hour per year. The capacity factor is 13.1%. The mean output 71 kilowatts. The wind penetration is 70.3%. And the hours of operation is 3,376 hours per year. The levised cost is about $0.2 kilowatt hours. And here is the some maximum output and the minimum output of the wind turbine results. The maximum output is 269 kilowatts and 0 is the minimum. The wind penetration was already I told about is 70.3%, and the total rated capacity is about 540 kilowatts. And the and this is done by the software Homer Pro. Now, moving on, electricity production summary. The PV production held about 68.2% because from March to October we are going to run on the PV because we get most of the sunlights during these days, and the wind penetration is about 30.7%, and from the diesel is only 1.5%. It may be because of some disasters or by any, if there is no sunlight and wind, so we can use a diesel generator maybe in emergency. And now talk the optimized design system, including the integration of renewable energy sources and efficient energy storage, ensures a reliable and sustainable power supply for the Philley Island. And the simulation result provide for from these results is valuable insight into the performance and energy production capability of the PV arrays, generators, and batteries system within the hybrid power system. The excess electricity production highlights the potential for the system to contribute to local grid and reduce dependency on conventional resources, fostering a cleaner and greener energy future. Now, this is the dynamic model of a system that we designed in the MATLAB. So this is the for Philley Island, and its components are the MATLAB simulation used to analyze the dynamic behavior of the integrative optimal framework for a hybrid power system tailored for a Philley Island, which is the name of our project. And the components are the main grid connection, rated capacity of about 154 megawatts, a voltage rating of 34.5 kilovolts. The step down transformer, lowering grid voltage to 400 volts for integration with the hybrid system. The primary energy source PV panels array 41 kilowatts, and the PMSG wind turbine system is about 1.5 megawatts. The diesel generator 430 kilowatts, and the control the MPPT for PV grid and machine side converter for the wind turbine diesel engine governor for the generator. Microsystems include supplies power to the two critical loads and one non-critical, other two specific power ratings. This simulation model is designed using MATLAB Simulink to analyze the dynamic behavior of the proposed our project name. The model comprises the several keys component to ensure the comprehensive evaluation of the hybrid system performance. And from the MATLAB simulation, we can see there are two critical loads in the down the two boxes, uh, and on the middle there is one non-critical load. The main grid is connected to the transformers, and the pinkish type box is the diesel generator. In the middle is a PV array, and on the right side is the wind turbine. Thank you. And now I'm going to give the slides to Mr. Saibit Singh.
Thank you, Sahil. My name is Sahibjit, and I will discuss the simulation results. So first, we will check on the wind powered system design of Philley Island. We have used PMSG, which is Permanent Magnet Synchronous Machine wind turbine, which we have installed on Philley Island in is a technically advanced and very good for energy solutions. With a rating power capacity of 1.5 megahertz and a standard uh, operation frequency of 60 hertz. This system is very good and will be very effective for the island. and we are thinking that this will be very good to harvest uh, wind energy for the PV uh, for the for the Philly Island. Uh, the supply of to the critical and non-critical node and the hybrid system of efficiency creating to the varying energy demand and enable a effective and stable power supply to the critical load. Overall results validate the effectiveness of the purpose of integration optimal framework of hybrid system in Philly Island. Um, and the combination of renewable resources and backup generator results in the effectiveness of the system. The wind system, the wind turbine combined about 1.5 megawatt of power showcase the successful harness of the wind energy and its effective integration in the hybrid. The diesel generates supply of supplies an additional power output around 25 kilowatt, illustrating its role for a very good backup generator. So this is now we will talk about solar design of Philly Island. So the main grid connected service with the primary source of the capacity of 154 megawatt and the voltage rating of 4.5 kilowatt. And this system hybrid system up uh, up down transform is included in the model to lower the grid voltage to 400 watt. The heart of the PV, the heart of the hybrid system consists of three primary energy source PV array, and the PV array rated are like 41 kilowatt and equipped with controlled uh, and very good uh, MPPT system. We are using P and O algorithm, which is considered as one of the best algorithm. The MPPT approach extend beyond the power output adjustment is included in the PV era and produce very effective and help to monitor the voltage and the current of the system. Here you can see that high index and low index is given in the high index is given in the blue and the low index is given in the high radiance is given in the blue and low radiance is given in a red, and which is like almost constant at high radiance is irradiance is almost constant at 40 and kilowatt, and whereas the low radiance is always almost constant at 50 kilowatt. And next, so this is our generator which we are using as a backup. So this will be only be used when there will be less wind, or we don't think of using uh, wind or solar system. So the capacity is of the generator is 410 kilowatt, uh, which at 430 kilowatt, the component integrates a diesel generator valve and acceleration system of stable power generation. The wind, the diesel generator is zero point 0.5 megawatt, as we have seen in the I have I told you before that it supplies an additional power of around 25 kilowatt, and it illustrates the backup and during the period of non-renewable is not available. Uh, so this were the all the basic results which we have taken out and from the MATLAB. And the here in the graph we can see that the initial load is and the load increase is almost constant, and our system is considered as very powerful for the future. Comparing with between diesel and solar power of Pilley Island reveals an important finding, and the economic and solar power system requires high investment, but it will be very effective, uh, as it will be good for the long run and low maintenance and low expensive. Overall, solar panel have a long lifespan than a diesel generator. Further, the it also will help as economic for the solar energy. This term, in terms of environment impact, the solar power system outstand a clean and sustainable alternative, as they produce zero emissions during the operation. Why, while diesel generator, as we all know, produce air pollution and gas emissions. Uh, this is the main purpose of our project, to make a hybrid system where we can showcase that how we can utilize our nature of sun and as a solar energy and wind to produce and um, to uh, j- to supply energy to the island, which is remote and there which is not that much connected to the grid. Thank you very much. Thank you for our presentation.